This is one of the major challenges of our field. How do we modulate graft versus host disease, the negative consequence of the transplant, yet retain graft versus tumor effects, the positive aspects of the transplant? And I showed you one approach of engineering the graft to bring out certain cell populations. We think that has great potential to do exactly what we hope to achieve, which is what we learned from animal modeling. There are other strategies that other investigators are exploring. One particular one from Seattle, from the Fred Hutchinson Cancer Institute, involves depleting so-called naive T cells, which we think are responsible for causing graft versus host disease. Another strategy done widely in Europe is to deplete so-called alpha-beta T cells and retain the other T cell populations. So there are a number of different strategies, and it's very difficult to know which one is the perfect strategy, and they may all work, and that's fine. The end result has to be documented in clinical trials, however. One of our challenges has been that the animal modeling is useful for defining concepts, but it does not prove that a particular therapy or a strategy is better than the next. So that has to be done through clinical trials. And that's the type of evidence that we need to really document that a particular strategy is better. Bone marrow transplantation is complicated. You're trying to do different things. And what we ultimately want is what we call GRFS, GVHD, relapse-free survival. And that's the ultimate goal. And a big part of our challenge is that we have no way to measure whether you've retained the graft versus tumor effect other than following patients and making sure they don't relapse. So it's hard work. It takes a long time, it takes difficult studies, and there probably is more than one strategy that will ultimately work. Well, you bring up a very interesting question. You brought up the concept of immune tolerance. So that's something that remarkably happens after a transplant, is that the donor becomes tolerant of the recipient. And I think that's one of the truly black boxes of what we do in transplantation. We know it happens over a period of months, and during that time, patients are at great risk for various infections. They have to be followed at a transplant center. They're on lots of different medications. They can reactivate all kinds of infections. So that's really one of the major unmet questions of how does immune tolerance occur and how do we accelerate it? It's a very important concept, but there's been relatively little success. Various strategies that have been looked at are various cytokines to try to accelerate immune recovery. But to date, none of them have really borne much fruit. So it's an area of ongoing investigation and still a lot of work that needs to be done to try to figure that out. Now, that could have obvious relevance in other settings. For example, we at Stanford have developed a concept based upon work from one of my colleagues, Dr. Samuel Strober, who combines bone marrow transplantation with solid organ transplantation. The idea being you induce tolerance to the solid organ. So there's lots of areas that could be helpful in, but we're left now with recognizing this occurs. It takes months for it to occur, and we don't yet know how to really influence it. That's a very big question, very important question. I would say that bone marrow transplantation is a great example of personalized medicine, meaning that we identify a donor based upon the personal genes, HLA genes that the patient expresses. So that's very much already a personalized medicine. How do we more generalize those concepts is very difficult because it does require very specific donors for a particular patient. And I think that highlights how important doing personalized medicine really is. I think as we learn more about disease, one of the unmet questions is, what is the graft versus tumor effect? How do we know which characteristics of the patient's disease is more susceptible to graft versus tumor effects versus other patients who may be more resistant? Will allow us to pick patients better. Which patients would benefit from these therapies better than other patients? And I think that's really a direction we could go in. But I would say that bone marrow transplantation is a great example of personalized medicine because of the need for finding specific donors. Let's not forget that in this field, one of the great achievements was developing the so-called National Marrow Donor Program. There are now 33 million people around the world who volunteered to be a donor for someone they've never met before, which highlights how far you have to go to identify the personalized donor for a particular patient. So it's a complicated problem, and we made a lot of progress, and we continue to search for better ways to identify disease risk and better donors for individual patients to reduce risk, and all that has to be characterized by very well constructed clinical trials. The other piece that I want to mention is that it's very important that we collect outcomes. I think that's another area where the transplant field has been far ahead of other comparator fields. For example, in the United States, we are required by federal law to report our outcomes. So we collect information, we collect data, and then we report it to centralized repositories. And that allows us to really assess how we're doing. How would we compare to other centers? And I think that's critically important.